You know, when you watch movies, thermal vision always looks so cool. Like, think Predator, right? That shimmering heat vision.
Oh, yeah, or the sensors they use on Star Trek missions. Seeing
Yeah,
heat signatures, energy sources.
exactly. It sees this whole invisible world. But then you look at, well, the thermal cameras we actually have today.
Bulky is putting it mildly.
Yeah.
They work. Don't get me wrong, they're essential in loads of fields.
Uh-huh.
But the optics, they're often huge, heavy, and really expensive.
Right. We've got smartphones thinner than a credit card, practically, but a good thermal lens still looks like, I don't know, a serious paperweight.
It's a bit jarring, isn't it?
It is. And that's really what we're diving into today. Why the bulk? We've shrunk everything else. What if, just imagine, you could replace that big, heavy lens with something like a thin film, flat, patterned with structure smaller than a wavelength of light.
Well, that's precisely the idea behind metaoptics, or sometimes called flat optics. It's a totally different approach.
Hmm.
Instead of using thick, curved glass or germanium to bend light,
Mm-hmm.
you use these incredibly tiny nanoscale patterns etched onto a flat surface, usually silicon. And these patterns, they can manipulate light just as well, sometimes even better.
So it changes everything. Size, weight.
Size, weight, and crucially cost. It turns the whole equation on its head.
Okay, let's unpack this properly. Our mission for this deep dive is to look at a huge step forward, basically proving these meta-optics aren't just lab experiments anymore. They're ready for mass production.
Yeah, we're digging into a really significant piece of work on making complex flat lenses, specifically for infrared, in a way that factories can actually handle.
This comes from a paper in ACS Nano, published just this year, 2025. The team behind it, it's Kai Sun, Xingzhao Yan, Jordan Scott, Junyu Oh, James N. Monks, and Otto L. Muskins.
And it's a collaboration, which is key here. You've got the University of Southampton, their Optoelectronics Research Center, the academic powerhouse working directly with industry, Teledyne Optic Ltd.
So not just blue sky research. They were focused on the how, right? How do we get these amazing tiny lenses off the lab bench and onto a production line?
Exactly. Their goal wasn't just another cool demo. It was about smashing those manufacturing bottlenecks, making it work on big wafers, the kind that automated semiconductor factories use day in, day out.
Okay, let's set the stage. What's the big problem with current infrared lenses? Why are they such a, well, such a pain?
It really boils down to the materials you need to even see infrared light, especially those two critical bands for seeing through the atmosphere, the midwave, MWIR, and the long wave, LWIR.
Normal glass is useless for that.
Totally blind to it. You need special stuff. Exotic, expensive materials like single crystal germanium or specific chalcogenide glasses like zinc sulfide or zinc selenide.
And I gather those aren't exactly easy materials to work with.
Not at all. Germanium, for instance, costs a fortune. Sourcing it reliably is tricky, and it's pretty fragile. But the real killer for high-precision stuff is its thermal instability.
Thermal instability. You mean it changes with temperature?
Massively. It suffers badly from something called thermo-optical focal drift.
Okay, translate that. What does focal drift mean in, like, the real world?
Okay, picture an autonomous car. It's got a thermal camera using a germanium lens to spot pedestrians at night.
Makes sense.
Now the car starts up, the engine warms up, the electronics get hot. That heat seeps into the camera. As the germanium lens heats up even a little bit, the way it bends light changes, which means the focal point literally shifts. Suddenly, the image isn't sharp anymore. The system loses its calibration. That pedestrian might just become a blur.
That's terrifying. You need complex systems just to constantly readjust the focus.
Exactly. Power-hungry, complex mechanisms just fighting the physics of the material itself. It's a major headache for anything that needs to be reliable over time. And temperature, think satellites, drones, military gear.
So meta-optics offer a way out. They're mostly silicon, right? Which is stable, cheap, everywhere.
Precisely. Silicon handles temperature changes much, much better. But the challenge shifted. It wasn't the material, it was making the intricate patterns needed on that silicon at scale. That's been the roadblock for years.
Right. The early successes, the really amazing tiny lenses, they use techniques like e-beam lithography.
Yeah, electron beam lithography. Think of it like microscopic engraving with an electron beam. Phenomenally precise, you can draw features just nanometers across.
It's slow.
Incredibly slow, like painstakingly slow. Great for making one perfect prototype in a lab. Absolutely useless if you need to make millions of lenses for, say, smartphones or cars.
So for mass production, you need the semiconductor industry's workhorse, deep ultraviolet lithography. DUV, that's what makes computer
That's
chips.
the one. DUV is designed for speed and volume on big silicon wafers, like 8-inch or even 12-inch ones, but DUV has its own demands, especially when you want advanced functions.
Like making one lens work for both MWIR and LWIR at the same time.
Exactly. To get that kind of complex behavior, you often need to pattern both sides of the silicon wafer, front and back.
Ah, the double-sided dilemma.
I see.
DUV machines like things perfectly flat and uniform.
Extremely flat, they project patterns with incredible precision. If you flip a wafer over that already has tiny structures on the first side, and maybe the wafer itself isn't perfectly uniform in thickness, even by less than a micrometer.
Less than a micron, that's tiny.
It is. But it's enough to throw off the DUV's focus and alignment for the second side. Standard DUV tools just aren't built for that kind of complex two-sided job without really strict, expensive wafer requirements.
So the team had to find a way around that rigidity, make the complex wafer look simple to the machine. What was their trick?
Their innovation, the one they proved is production-ready, was a really clever fabrication process on standard 200mm silicon wafers. The key was using a double hard masking technique.
Double hard masking.
Yeah, it involves putting down a super thin layer, less than a micron thick of silicon dioxide, SiO2, before the main patterning step. This thin layer basically smooths everything out, makes the surface look perfectly flat to the DUV system, even if there are patterns underneath or slight wafer variations.
So it kind of hides the complexity.
It masks the complexity, exactly, and it makes the whole process compatible with the standard automated DUV track systems that industry already uses. They didn't need a brand new custom DUV machine.
That's smart. They adapted the process, not the multi-million-dollar tool.
Precisely. But here's the bit that really impressed me, the manufacturing wow moment. Aligning the patterns on the front side perfectly with the patterns on the back side.
Yeah, how do you do that accurately across a big 200mm wafer? Normally you need special markers inside the wafer, right?
Usually, yes.
Yeah.
Complex markers etched through the silicon, which adds steps and cost. This team, they didn't do that.
No. What did they use?
They used the standard wafer notch.
The what now?
You know that little semicircular cutout or flat edge that silicon wafer manufacturers put on every single wafer? It's just there for handling and basic orientation.
Yeah, they use that little notch for nanometer scale alignment.
They use that simple pre-existing notch as their primary reference point to align the front side pattern to the back side pattern. It's kind of an audacious engineering shortcut.
Hold on, that feels risky. Using a relatively crude feature on the edge to get micron-level precision across the entire wafer. How could they be sure that notch was accurate enough for Teledyne Quactic, their industrial partner?
That was the gamble, and they made it work. They developed a process to correct for any slight rotation based on that notch,
Yeah.
and the results. On their key demonstration wafer, wafer V5, the absolute alignment error between the front and back patterns was less than 10 micrometers.
10 micrometers, that's like the width of a red blood cell. Or a speck of dust.
Pretty much. And remember, that wafer is 725 micrometers thick, so 10 microns misalignment. That's less than 1.4% of the wafer thickness.
Wow.
Achieving that level of precision using existing industrial tools and a standard feature like the notch. That's what signals this is ready for prime time. Manufacturing solved.
And that manufacturing breakthrough is what enables the really cool stuff, like the independent dual band control you mentioned, one flat lens doing two jobs.
Right. That was their big application demonstration, making a single lens work efficiently in both the mid-wave infrared, MWIR, think 3 to 5 microns, and the long-wave infrared, LWIR, or like 8-12 microns.
And controlling them independently? Why is that such a big deal?
Well, different infrared bands tell you different things. LWIR is often better in fog or rain. MWIR might give higher resolution for tracking hotspots. Being able to optimize for both, or even focus them differently, with one single, simple lens. That's incredibly powerful. Traditional optics need complex assemblies to do that.
And you said the double-sided patterning was crucial for this. Couldn't they do it with just one side?
Not easily, especially for the LWI band. The wavelengths are longer, so you need to impart a bigger phase shift to the light to focus it properly. A single layer of nanostructures just doesn't have enough optical power, if you like.
Ah.
By splitting the job, putting some nanostructures on the front and some on the back, they can collectively achieve the large phase shift needed for LWIR and tune the MWIR focus independently, using the specific shapes of those structures. They use things like hollow squares and filled squares at different scales.
So what specific lenses did they make to prove this concept?
They fabricated 3 distinct metal lenses. All 3 were designed to focus the MWIR light at 4 microns, perfectly at a distance of 25 millimeters.
Okay, MWI fix.
But for the LWIR light at 10 microns, those same three lenses were designed to have different focal lengths. One focused at 20 millimeters, one at 25 millimeters, and one at 30 millimeters.
So the same physical lens focuses the two heat colors at different spots, based purely on the nanoscale design.
Exactly. Independent control. That kind of multifunctionality from a single flat component is something conventional optics really struggles with.
Now, to really prove this wasn't just a tiny lab chip, they needed to make bigger lenses, right? Something you could actually put in a camera.
Absolutely. The DUV tools have a limit on how large an area they can pattern in one go the field size. So the team used a technique called multi-exposure stitching.
Like making a photo panorama.
Pretty much, yeah. They stitched together multiple exposures side by side to create a much larger functional area. Using this, they fabricated metal lenses with a practical diameter of 40 millimeters.
Okay, 40 millimeter, that's a usable size, getting into real-world territory.
Definitely. Big enough to integrate into actual commercial thermal camera systems.
And did they? How did these scaled-up lenses perform?
They did. They laser cut the 40 millimeter lenses out of the wafer and tested them thoroughly. The performance was frankly outstanding. They used interferometry, a super precise way to measure optical quality, and confirmed the lenses were diffraction limited.
Diffraction limited. That sounds important. What does it mean for us non-physicists?
It's basically the ultimate seal of approval for a lens. It means the lens is so perfectly made, its ability to form a sharp image is limited only by the fundamental physics of light itself, how light waves naturally spread out. It's not limited by manufacturing flaws or material issues.
So it's as good as physics allows.
Pretty much. They measured the Strehl ratio, which quantifies this. A ratio above 0.8 is generally considered diffraction limited. These lenses hit 0.90 for MWIR and 0.93 for LWIR.
Wow. So the production process, the scaling, the alignment, it all worked beautifully.
Yes, it proves the method is robust enough for high-end applications, defense, industrial inspection, autonomous systems. They even put them in cameras and took thermal images of things like soldering irons and hands, showing real-world function.
I also saw they tackled another potential issue with flat optics head-on, something called chromatic dispersion, that rainbow fringing effect you can sometimes get.
That's right. That's a known characteristic of metal lenses, different colors, where wavelengths tend to focus at slightly different points. It can blur the image. But they didn't just say, okay, here's a great lens, deal with the dispersion. They showed how to fix it by thinking about the whole system. They showed you could pair their metalens with a simple, conventional refractive lens made of a specific material, barium fluoride, BabyF2.
Why barium fluoride?
Because, cleverly, BabyF2 has the opposite chromatic dispersion signature compared to the metalens. One spreads the colors out one way, the other spreads them the opposite way.
Ah, so they cancel each other out.
Exactly. Put them together in a hybrid system, and the overall color fringing is massively reduced. The image quality gets significantly better. It shows these new flat lenses won't just replace old ones. They'll enable smarter, lighter, hybrid optical systems.
This really feels like a major turning point. This work from Sun, Jan, and the team seems to bridge that gap between lab potential and industrial reality.
I think it does. So let's boil it down. What are the big takeaways here?
Okay, takeaway number one for me. Metaoptics are ready for the factory floor. Wafer scale production, large diameters, using standard DUV tools. This tech is moving out of research labs and into the actual supply chain.
Agreed. Takeaway two. That double-sided fabrication is the key enabler for complexity. The clever masking, using the simple wafer notch for alignment that unlocks powerful functions like controlling MWIR and LWIR independently in one flat component, that's huge for next-gen sensors.
And takeaway three, the performance is there. Achieving diffraction-limited quality means these aren't just curiosities. They're high-precision optics ready for demanding jobs in cars, drones, industry, defense, you name it.
Yeah, the quality is undeniable. This manufacturing success really blows open the design possibilities for meta-optics. We're not just talking smaller thermal cameras anymore.
What else could we see?
Well, imagine integrating other functions directly onto the lens surface, maybe built-in anti-reflection coatings based on moth-eye structures or complex correctors for specific optical aberrations, all patterned onto that single flat piece of silicon during manufacturing.
It really shifts the paradigm from assembling multiple bulky parts to designing one highly integrated, smart component.
Precisely. It's a whole new way to think about building optical systems.
So here's the final thought to leave you with. If mass production can make these incredibly complex, specialized optics cheap, thin, light, and stable, What kind of sci-fi level optical challenges might suddenly become solvable? Think ultra-thin cameras seamlessly integrated into glasses, or maybe advanced medical sensors that can see deeper or clearer inside the body without needing bulky machines. What's next on the horizon now that the factory doors are open? Something to ponder until our next deep dive.